How are you guys doing?
Good.
Have a seat. Relax.
Absolutely, sir. It's another Monday.
Monday. Good. You will learn more quantum mechanics today. Oh, I hope so. All right, any questions? Anything? No? All right, so we looked at the particle in the box, right, last time. I just want to go over some point that I made relatively quickly in the last lecture, and that was about momentum and kinetic energy, right? So kinetic energy, average kinetic energy for any wave function which is normalized is given by this expression, right? And this is the same as if the function is in 1D as integral over psi star t psi, right? Psi depends on x, may depend on t. T dependence really doesn't change much because our kinetic energy operator is square of the momentum operator, right? And if we write it down explicitly, it's a derivative with respect to spatial coordinate x, so there's no time dependence. Okay? Now, in classical mechanics, in contrast, T classical is classical momentum, right? And then this thing, or mv squared divided by 2, right? So both p classical and v classical, they potentially are function of time, right? So because the momentum and velocity of the object that we consider in classical mechanics, they may depend on like time, right? Now in quantum mechanics, the operators that we'll be dealing with, they are not dependent on time, okay? And the time dependence comes only through the wave function. Now, for a particle in the box, we found that the function is square root of 2 divided by L sine of n pi x divided by L, right? So that was particle in the box functions where n is any number from the range 1 to infinity. Okay? And so these functions have no time dependence, and yet the kinetic energy, average kinetic energy for them is equal to energy of this function, right? Why is that? Why average energy is so simple? Why can I just, instead of considering all these integrals, I can just write it down like this?
Because n is restricted.
No, and it can be anything from 1 to infinity. Well, pretty much I wrote an equation where there's a left-hand side, one symbol, which I defined, and the right-hand side, another symbol, which I haven't defined yet. So why not? A equals B, always right. As long as A and B are not well defined, then A equals B, you can always claim that, right? So what is the En here? So En is the quantity that we obtained previous lecture. That's the eigenenergy corresponding to our particle in the box function, right? Remember we considered the equation, which is time independent Schrödinger equation, right? And we obtain for particle in the box, we have wave functions, sine functions, and energy expressions given by these expressions, right? So now the question is, why can I write that kinetic energy of particle in the box function is equal to its energy? On the left-hand side, I have kinetic energy. On the right-hand side, I have total energy. Yeah. There's no potential. Why there is no potential?
It's the way we set the experiment.
What experiment?
Or rather the criteria for the particle block.
Right? So all the information about the system is in this H part, right? So what was H for particle in the box? It's kinetic energy plus the potential formally is there, but it was given as infinity outside of the box where there is no function. And 0 when and there is no potential. Essentially, the situation is that there is no potential where we have a function, and there is no potential where we don't have a function. So there is infinite potential where we don't have a function. So technically, we kind of don't have potential, but the potential, since it's still non-trivial expression, it's not like we are considering the situation where potential is 0 everywhere, right? So this type of potential just creates the boundary conditions. That boundary condition means that the function that we're looking for, it must have certain values in a certain values of the coordinates, right? Do you follow? No? No idea what I'm talking about? Nothing to write down. It's all in the notes. Just try to understand. So what's the difference between this trivial case where there is no potential and this case where there is no potential in the box and there is infinite potential outside of the box? So it seems like these two cases are very similar, but there is a difference. Because this case makes us to look for the function which has non-zero value only inside the box. While this potential, which absence of thereof, essentially will not restrict us, and we can look for the function which is finite everywhere, or in some range, doesn't really matter. So this doesn't restrict us. This one restricts us, but it doesn't provide any potential in the region where we look for the function, right? So, and that's only sets that the function at 0 must be 0, and the function at L, at the boundary, also should be 0. In between, it can be anything. Outside, it should be 0, right? So this type of potential requires for the function to have such restrictions. This, and the fact that the function is 0 outside of the box, right? So, but all the energy is pretty much kinetic energy, this part, because potential is 0. We can do this more formally and say, all right, what is our potential energy, average potential energy? So what would be the formal expression for this? Do you guys know how to substitute T for V? You know, it's like a very simple game. Wherever you have T, you put V, and then you have an answer. Right? So you see their expression, psi, T, psi. So all you need is to substitute T for V, and you get the corresponding expression for V. Why? Because quantum mechanics is very simple. You have properties, they have operators. You change the operator, you get a different property. Right? It's like student 1 has a name, say John. You change John to Michael, you get another student. Right? So very simple. Same with the operators, T, V, but the essence is the same. Okay, so what's then? This is integral from minus infinity to plus infinity, right? Function star v dx. And this integral will consist of 3 parts. Zone 1, zone 2, zone 3, right? And in zone 1, the function will be 0, potential infinite. 0 times infinity, in this case 0. Not all mathematicians would not like that type of talk. But we can always say that we may consider infinity of the potential as a limit from the finite value of some kind, and then, yeah, it will be 0. And then there is region 2, where we integrate from 0 to L. Function is non-zero, but it's multiplied by 0 potential, right? Because we have potential 0 in this region. And so this is also going to be 0. Region 3 is the same as region 1. So we have 3 zeros together. They give us 0. So that's why average potential energy is 0 in the particle in the box problem. And so we know that any energy is, you can always write average energy equal to, well, average essentially Hamiltonian, right? And what is this? It's psi t plus v. Now we substitute t by t plus v. And since this is just an integral, sum of integral of the sum is equal to sum of the integrals, right? So we can write this as psi t psi plus psi v psi, right? And this is 0. We just showed that. So all the energy is a kinetic energy, right? So this is average kinetic energy, and this is our energy. So that's why we can write for any function like this, depending on n, of course, we have a kinetic energy equal to some non-zero value that comes out of the solution. Okay? So we have a function that is stationary, so it's not moving anywhere, doesn't depend on time, and its kinetic energy is non-zero. Which is kind of interesting because in classical mechanics we always think about non-zero kinetic energy. That means that something is moving. Here nothing moves, kinetic energy is non-zero. Why is that? Someone asked me what's the simplest possible explanation. Why do we have? Mathematically, the kinetic energy is an operator which is a second order derivative, right? And so this applied to any function that has a kind of curvature. Curvature comes from the second or higher degrees in the expansion. If we expand psi of x in the Taylor series, say around some constant a, then there will be linear term x minus a, right? Psi prime at a plus 1/2 second derivative at a multiplied by x minus a square plus so on and so forth. So if you have any derivative higher or equal than the second one, that's what produced the curvature, right? Because these terms, the first derivative and the constant term, this is just a line, the equation of line. You have x in the first power and the constants, right? So that's line. Whenever you have some curvature, that means you have a second derivative. That already has a second power here, or a third and fourth, so on and so forth. So whenever we have a wave function that is curved, then the kinetic energy will be something non-zero. Okay? So that's the case here because we have boundary condition. Wave function must be 0 at the point. Now it must be something also in between. So there is no way you can connect these 2 points with something in between. well, there is, I guess, one way would be the straight line, but the problem with that solution would be this point where, or, well, there are multiple solutions, right, of that kind, some kind of broken lines, right? But the problem with this kind of solution is that the first derivative is positive here, first derivative is negative here, and so if you plot the first derivative of this function, it will have something positive here, then go into something negative with a sharp kind of breakdown, right? So that will be the graph of the psi prime. And then you won't be able to differentiate this second time, so the function is no good for our purposes. So we didn't get such function. So we got something curved that connected this line with that line. So that's why kinetic energy is not zero. Now, if we consider, on the other hand, momentum, I pointed out at the previous lecture that if you have a function which is real, then the momentum will always be zero if, let's properly write this, imaginary part of wave function is zero. Right? So function, general function can be always written as sum of two real functions, f of x plus I times g of x, right? Just any function psi of x. And so this condition, imaginary part of psi, is essentially function g of x, and that must be zero. So that's the condition. So you don't have anything with I in it, okay, or in front of it. So for any function like that, the momentum will always be zero. And so I went through this relatively quickly. Now I wanted to clarify why is this happening. And let's just recall that what is momentum? Momentum is, and this will be very essential, it's the operator that has derivative, right? That's why this derivative, well, this differentiation gets into kinetic energy, and the whole quantum mechanics become kind of a little bit complicated because of the derivatives involved. But okay, so here momentum will have derivative, and we have also this part, which is imaginary unit multiplied by h bar, right? So this overall is imaginary number, right? What we know about any operator in quantum mechanics is that if you have a wave function, you make an average. What's the, how can we obtain this average? Can we obtain it in experiment? Say again, please.
For average?
Huh?
For average, you said?
Yeah, well, this average, right? We can calculate it, but the question is, okay, say we calculated, got the number. Can we get the same number out of the experiment of some kind?
Sure.
Yeah. So how do we do it? Like, not the measurement itself, but say if we do, how many measurements do we need to make in order to obtain the average that we calculated? Infinite or big number, right? Essentially, you get, say, you start measuring momentum, and you start making a histogram, and based on this histogram, there will be average somewhere, right? So it's a real number, p average, so it can be obtained in an experiment. So it should not be complex, right? It can be negative, positive, depending on which way the function, like a particle in this case, flying. This way, positive momentum, that way, negative momentum. Could be positive, negative, doesn't really matter. But the imaginary part of this number should be zero because, well, all the measurable quantities are real. Okay? So now, if we keep that in mind, let's just consider integral over any function which is L square integrable psi and real. Right? So we will consider integral with the momentum operator, d over dx, right? Psi of x. And I'll show you that, well, this integral will be 0 for any real function. How do I do that? Without knowing what the function is. Well, first of all, I can take this minus IH bar outside of the integral, right? And at this point, you might think, okay, so what do we have here? We consider an average of the momentum, right? So this quantity must be real. We just established because it's producing something that is measurable, this thing must be real, right? And if we analyze what this quantity is, this thing is complex, definitely, right? Complex. And this thing is real. Why do I say that this is real? Because function is real, right? So function is real. When you differentiate a real function, you get real derivatives. Right? When you multiply real derivatives with another real derivative, multiply by another function, which is also real, conjugation doesn't really mean anything. If you have a real function, conjugation can be removed. It's not going to change anything in the function because there is no I in the function. Right? So this whole thing is real. So now, using the simple logic, if this is real, but it's equal to something complex multiplied by something real, the only way we can keep this real is this real number should be 0, right? So it kills the complex part. That's the only way. You cannot, how can you remove I otherwise? You can divide by I, but that would require having I here, right? So you could try to do something like division by I, but then 1 over I, that's what I'm doing here, should be out of this, like should come out of this integral somehow. But we established this integral should be real, right? So it should not contain any I. So the only way to kill this I is to multiply this term by 0. And that's what will keep the momentums real, right? There is, of course, more elaborate way of showing that this is 0, and it's quite a kind of easy way. You know all integration by parts, right? So let's just do the integration by parts of this expression, right? So we call, let's say, this thing I integral equal to integration. By I mean just the integral, so just not to add more minus and i's into this whole thing. Let's just consider the integral itself. And integration by parts tells us that, well, psi square from minus infinity to plus infinity, that's the part that comes out of the integral, minus, and there will be, well, derivative goes to this side, and there will be, again, d psi dx, psi dx, right? But look, here we got, out of this integral, we got something, and this integral again, right? This is again I. It's just before we differentiated this function, multiplied by this function, but the functions are the same. So that's why, like, if you differentiate this function, multiply by that function, it's the same integral. Now, we got I equal to minus I, because there is a minus here, and there is this part. And my claim is this part is 0 because it's the value of function at the infinity. In order for the function to be integrable with its square, it must decay to 0 at infinity. if it goes to the finite values at infinity, that means, well, before it gets to the infinity, you keep integrating, and that will contribute to the integral.
Yeah, doesn't that violate one of the properties of a wave function?
Yeah, I'm explaining why is it violating it. All right. So the property of the function is that psi squared dx from minus infinity to plus infinity should be less than infinity, right? So it should be finite. But that cannot be achieved if the function itself is something finite on the infinities, plus or minus. So this necessarily should be 0. And then we got I equals to minus I. And the only number that satisfies, the real number that satisfies this condition is that I must be 0 then, if number equals to minus itself. So this is 0, and that concludes the proof that any real function will have average momentum equal to 0, including, of course, particle in the box. So then if you square that 0, then you, of course, get 0. An interesting thing happens is that on one hand, average kinetic energy, which is p squared divided by 2m averaged, right, is non-zero. And then p average divided by 2m, this thing squared, this will be 0, right? So note the difference here. I first squared the momentum and then averaged it. Then it will be non-zero. But if you average momentum first with the wave function and then square and multiply by some constants, then you get 0, right? So here's the situation. Okay. Now let's consider a couple of examples. Say for a particle in a box. Example number 1. Let's say we have a function which is a superposition function. That means function itself is not an eigenfunction of the Hamiltonian, and it's given by linear combination of particle in a box functions. Right? So these guys are particle in the box functions, and they are normalized. Everything is good. Function itself may be not normalized. We'll check that. The eigenvalues corresponding to these functions are E1 and E2. And the question is, if we measure energy, what are the probabilities to get this value and this value? And to make it more interesting, what is the probability of getting this value? Anyone can answer right away?
Squared.
With one stone, two birds, huh? It indeed coefficients. Well, can you explain your logic? Lecture notes. See lecture notes. Well, why can we? Okay, so P1 in this case would be what? 5/9, right? So why? Like, what's our thinking? Why can we do this? Okay. But first of all, we have a superposition, right? And we're interested in energy. We can go through the same kind of logic that energy has no operator, right? The lone way would be the following. Energy has an operator. Operator is a Hamiltonian, right? Hamiltonian of this system is particle in a box Hamiltonian, right? And we know that it has eigenfunctions, h psi I, right? ei psi I. Then the next step is, once we establish Hamiltonian and we know its eigenfunctions, the function that is given, is it an eigenfunction of that Hamiltonian or not? Yes or no?
No.
So you think yes? No?
Who said no?
Well, let's just check, right? I am teaching you so that you can check, right? So it's like that instead of putting square root of 5 divided by 3, I put alpha, and 2 divided by 3 is beta. So I have alpha psi 1 plus beta psi 2. And so this operator acts on this thing, and then plus there will be action on the second term, right? So the constants will not be affected by the Hamiltonian because Hamiltonian contains some functions and derivatives. So constants can be put aside. And so we have this expression, right? And so then we know how h acts on these guys because they are eigenfunctions. So they are simplest function for the considering the action of the Hamiltonian. And so we will have E1 psi 1 plus beta E2 psi 2. And so then the question is, can we write this down as some E multiplied by phi? Can we? No, because E1 and E2 are different, right? So that's why you cannot write the common energy. So that means this function is not an eigenfunction of the operator. So you need to go by the second branch and expand it in the eigenstates. That expansion is already given. So that's the easy. That's kind of the easy subpath of the second branch. All right. And the only thing you need to make sure is that the function is normalized, right? Because if the coefficient, if I multiply like this coefficient by 100 and this coefficient by 200, so then this square of these coefficients will be way higher than 1, right? And but we know the probability should be below 1, right? For the two events, so they all should be lower than 1 or equal to 1, not more than 1, okay? So let's make sure that this function is normalized. So then we can just take the coefficients and square them. How do we check that the function is normalized? So we multiply function by its square. Wait, function by its square?
No. Sorry, square is a function.
Square the function, okay. All right, and so what do we do next? Integrate. From where to where? Okay. That's a safe choice. Although if it's particle in the box, then we can only 0 to L, right? Or whatever box size is. Sometimes in these problems you may, although in this course I always will be using 0 to L, but in some other considerations could be from minus L to L, and then the solution will be slightly different, but in essence it's the same. Okay, but from minus infinity to plus infinity it always will work. And so then you can present this in a short notation like this, and then we can, what do? We put the explicit function inside, right? Okay. And so what's next? We do the algebra, right? So we have terms like psi1, 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 psi2, psi2, psi1, and psi2, psi2 with coefficients 5 divided by 9. This one with coefficient square root of 5 times 2 divided by 9. This also with the square root of 5 times 2 divided by 9. And this one with 4 divided by 9. What's next? Is this one? Looks like more complicated. Are you asking me? The question was, this sum, is it 1 or not? It is equal to 1. Would you care to elaborate? Because this doesn't look like 1 to me. Okay. Why? Huh? Right, it's orthonormal functions, right? So any two different functions will give the zero integral, right? So we should forget about these terms. And based on orthonormality, these guys will be 1, and this one also will be 1. So we got rid of the integrals. And we have 5 over 9 plus 4 over 9, right? So this is 9 over 9, and this is 1. So yes, you're right. So the function is normalized, right, already. You don't need to do anything, but you can just square the coefficients. And now let's see. The probability of getting this result will be coefficient 1 squared, 5 over 9. And probability of getting this result, P2, will be 4 over 9. And the probability of getting this result, 0. So 217 is equal to 0. And any other result for that matter. The only two results you can get if you measure energy of the system which has this function as a kind of function representing the state of the system. Okay? And we also can calculate what would be the result of the average for the energy, right? So how do we do that? We can do it in two ways. Just a brute force integration. Not suggesting that, especially on the midterm, because, well, there's just a few terms to consider, a few integrals to take. It's so much simpler if you do in algebraic way, which is actually you can either consider that h phi is the same as h of alpha psi 1 plus beta psi 2, right? And then it's alpha e1 psi 1 plus beta e2 psi 2, and then the integrals that you need to take, they will consist of integrals of the functions which are orthonormal, and that's easy. Just don't forget about the coefficients. In an even simpler way of doing things would be, we know the probabilities, and so average energy is just the sum of probabilities multiplied by the values, P1 times E1 plus P2 times E2. That's the easiest way to calculate average, right? So when you have a representation of the wave function as a linear combination of eigenfunctions, then calculating average is just simpler that way, because you already know the probabilities, usually from the coefficients. It's only when the function is not normalized, and it's probably not going to be normalized on the midterm, you need to make sure that you know how to, well, normalize these coefficients, right? So for that, all you need is just to square this, plus square of that, take a square root of that, and divide each on that number, right? And you will get a normalized wave function. Do you guys follow, or should I? It's essentially, in some of the lecture notes, I presented that, okay, let's say there is a wave function that is alpha times one eigenfunction plus beta times another eigenfunction plus gamma another eigenfunction. And then I showed how do you make alpha square plus beta square plus gamma square, take a square root of that, divide alpha, beta, gamma on that square root, and that will give you already normalized function. So if you still confused about that, let me know. I'll be happy to explain it again. All right, so let's consider another example, which is more interesting. So we'll consider a situation where the wave function, I already kind of given you that wave function. It's one of the simplest functions that is not an eigenfunction, right? And zero otherwise. The question is, what is the, let's say, what is the probability of getting E1, where E1 is the first eigenenergy of particle in a box, where length of the box is L, and the function that represents our system is this function, and we know that this function is not an eigenfunction. For those who missed that part, the check is very simple. You apply Hamiltonian to this function. Hamiltonian is essentially kinetic energy, because it's already boundary conditions are taken care of. So second derivative will just make a constant out of this function. So you will not get something like t phi equals lambda phi. You will get only t phi equals some lambda. And so that's not the situation where phi is called the eigenfunction of t, right? So in this situation, we can always write phi as a linear combination of eigenfunctions, right? And the question here is, what is the probability of getting, if we do the measurement of this function, what will be the probability of getting the first eigenenergy, which is h square pi squared divided by 2 ml, right? So this value. So what do we need to do to obtain the probability of getting this value when we measure energy of the system that is described by this function? What do we need for that, to get that probability? Coefficient, that's right. So what coefficient?
The probability is given by the square of the coefficients.
Right, but which coefficient? There are infinite number of these coefficients, right? For one, right? So each coefficient corresponds to the eigenfunction, and every eigenfunction corresponds to h psi I equals ei psi, right? So each eigenfunction corresponds to eigenvalue for the operator that we're interested in, and the eigenvalue which we're interested in is number 1. So that means eigenfunction that corresponds to this eigenvalue is also 1, and the coefficient is also 1, right? So that's why we need C1 absolute square, and that will be the probability in experiment to get E1 when we measure energy for the system given by the function phi, right? Yeah, sometimes these statements are too long, but that's what it is. All right, so how do we get this coefficient? No idea? Well, it's very simple. It's like with vectors. You multiply and integrate to make an inner product this function and this expansion, right? By, say, something. Let me show you some magic. So if I multiply with psi1 star and integrate from minus infinity to plus infinity, I'll do that on the left, and I'll do the same thing on the right, right? Because that's the only way it's fair. So equals to, and then psi1 star, right? So I do that. Say this is something which I'll tell you in a moment what it is. But this part can be rewritten by taking the sum outside of the integral, right? And taking the coefficient outside of the integrals because they don't depend on x. And inside we have integration psi1 star, psi I, and they both depend on x, right? And now these are orthonormal functions, right? So then these integrals will be all 0, and only one of these integrals will be 1 when I equals to 1, right? So the only one survivor will be in that sum, and that is C1. So C1 is equal to this integral. Simple algebra. C1, that's what we got, because of orthonormality, is equal to this integral. So, and I think I gave you the definition that Ci generally equals to the integral over psi I star multiplied by, well, the function that you have, right? So that is general definition, how to find the coefficients, and that works because of this chain and the fact that the functions are orthonormal.
That is a requirement. They have to be orthonormal for them to work.
Right, because if they are not orthonormal, then you will not kill the terms, the other terms, right? So you have C1, C2, multiplied by something. Here, the fact that they are only 0 and 1s, and only 1, 1, only when I is equal to 1, that allows you, out of the infinite number of terms, single out one term that you need, right? By that trick. It's called projection, essentially. What I did here is I projected in vectors. That would be, I have a vector phi, and I have a coordinate system, x, y, z, and I did the inner product of one of my vectors. Say I'm interested in how high my vector phi goes, and for that I need a projection of that vector on the vertical axis, and that would be this distance, right? So that's what I did here. By this inner product is essentially, geometrically it's calculating the projection of, this is my basis vector psi1, which would correspond to some geometrical vector. If we talked about the three-dimensional vectors, then that's what would happen here. But in reality, we're talking about wave functions, and in some basis of other functions. So that's the geometrical meaning kind of is harder to visualize in terms of functions, but if they were vectors, that would be the meaning. We just do the projection to find the coefficients. Okay, so it's infinite dimensional space. You cannot imagine it. Right? So anything beyond 3 dimensions, it's hard to imagine. Here we have infinite dimensions, but formally, the way we do projections is given by integral instead of well, it is inner product, and that's why it works. So just formal procedure. All right, so now let's finish that formal procedure. So we just need to take the integral to get the coefficient, right? And integral is relatively simple. So if we put all the coefficients together outside of the integral, this is 2 divided by square root of L, square root of 2 divided by L. That's from here, from our functions, right? 30 divided by L into the 5th square root. That's from our function phi. And then here we have 0 to L. We don't need to consider all the range from minus infinity to plus infinity. Then our function. Sine 1 pi x, and 1 can be removed. Right, so that's the integral you need to consider. And of course, you guys are very good with integrals. So you can tell me right away that C1 is 8 multiplied by square root of 15 divided by pi cube. Right? It's obvious. In reality, of course, in the notes, I have all the integrals written out. You can see them. Yeah.
Clarification.
Yeah.
Where did the exponent find L?
Exponent of pi. Pi cube?
No, above that. See, it's L to the pi. 30. 30 over.
This one?
Yeah.
Oh, yeah, good point. I forgot to put it here. It is actually part of the coefficient. Yeah. Yeah. So if you, and I think we even did this at some point. If I start with a function which is just x times L minus x, and I'll try to normalize it, actually it will be square root of 30 divided by L to the 5th. Right. So that's where the 5th comes from. And this number, 8 times square root of 15 divided by pi cube, it's actually very close to 1. It's 0.9939277. Something else. Right, so what does this mean is that it means that that function, our function, is actually very, very similar to first eigenfunction, right? The overlap, the way the function looks like, is very close to 1, so that means it's actually very close to sine function. And so the probability is not this value, but the square of that value. And P1 will be, as you can imagine, also very close to 1. Let me put it here. P1 equals to 0.9986. Right, so it's very close to 1. All right. So now let me show you some movies. And the movies will be about this type of functions. And also related to kinetic energy and eigenstates, non-stationary states, superposition states, that sort of stuff. So the little experiment that I want to show you, numerical experiment, is this function, this one, the one we considered. It looks like the first eigenfunction, so it looks like this, right? And if you start solving time-dependent Schrödinger equation, right, where psi of x will be initial condition, right, at 0 time. In time-dependent Schrödinger equation, we are looking for time dependence of the wave function. And we can start with anything that is good for boundary conditions, or in terms of boundary conditions. This function is a good for boundary conditions. It ends at 0, so at the boundaries of the box. And so we can start with that and solve for, well, this time-dependent Schrödinger equation. And the solution is always very general once we have expansion like this. And I showed you how to find the coefficient 1. You can find by the same technique any coefficient. And that's what my program actually will be doing. Not up to infinity, but up to some large value. So you can expand this function as a linear combination of eigenfunctions. And then time dependence, as we saw, comes in this form of the imaginary exponents. So essentially, once you know the coefficients, we know these guys, the eigenfunctions of the time-independent problem, h psi I, e I psi I, right? So once you do this expansion, then the time dependence obtained by just adding these exponents. And in the homework, you saw there was a sine function times the imaginary exponent. And in the second example, there was 2 sine functions multiplied by different exponents. So that's essentially the similar story. We just introduced the time dependence. It's introduced in such a simple way because we have expansion of the wave function as a linear combination of eigenfunctions of this problem. If we didn't know the solution of this problem, writing the time dependence of the just general function would be difficult, right? But once we know the solution of the time-independent Schrödinger equation, we always can solve the time-dependent one. Of course, under assumption that the Hamiltonian is not time-dependent. That's the only case when we can actually formulate time-independent Schrödinger equation, right? But then through the expansion, we can get this guy, and from this we can form the psi square and its time dependence, and that's probability density where the particle is, essentially, right? Now, we can start with this function here. But as you know, through our consideration, in this expansion, the first term will be large, others will be very, very small, right? Because, well, simply they must sum, like their square must sum up to 1. And the first term already picked like 99.9% of the expansion, right? So for the rest, it's just small. But then what we can do, and that's what my program will do, we can start making this parabola, which is here, smaller and smaller. Like we can squeeze it by a certain ratio. So I will just generate a series of functions which will look like this. 30 divided by L, and L will be divided by K. And to the 5th power, L minus L divided by K minus X. And so that is going to be my functions. So what do? They essentially when k equals 1, this is this function. When k equals 2, it's going to be a function where we have a parabola on the half of the box, and here it's going to be 0. So, and then L equals 3, the parabola will look like this, right? And so on and so forth. We can keep squeezing the parabola. And well, one outcome of that, if you just consider the average kinetic energy as a function of k, it will be proportional to k squared. So the higher the coefficient here, the kinetic energy will grow. And that you can think of as a reason, again, why electron doesn't follow the nucleus, because nucleus is very small. And so for electron to fall on the nucleus, it's like this experiment where k would be 10,000, right? So then the kinetic energy, the average kinetic energy of this, or even tighter wave function, will skyrocket, essentially. And of course, for any k, we can do this procedure, expanding the wave function in linear combination of eigenfunctions, putting the exponents and seeing how they're going to evolve in time. That's what my program will do. And you can see that the tighter we squeeze, the faster they will sprint back, okay? Because just a lot of energy is kind of stored when you squeeze the wave function, and that kinetic energy will, of course, try to, well, evolve, and will make our function to go in the box crazy. Okay, so let me show you that. Oh, that's too dark. Yeah, good. All right. Now let's make this k equals 1. And just a second. All right, so this is right here. This is a probability density, and you see it's barely moving. Well, it doesn't move very much, because essentially the expansion only consists pretty much the first term. And we almost have an eigenstate, and eigenstate is a stationary state, so the probability density has almost no dependence of time. So now this here, red and blue, the red dash curve is essentially the representation as a linear combination of eigenfunctions, and the blue one is a regional function, so they kind of lie on top of each other. And that just shows that we are good at representing the eigenfunction, like the original function as a linear combination of eigenfunctions. Now this plot shows a logarithm of coefficients in that expansion. And as you can see, numbers are a little bit small, but essentially all of them less than 10 to the minus 2. It's a first coefficient which is close to 0, which means logarithm of, well, 1 is close to 0, right? So the first coefficient is big, and then others, especially the even and odd, here there is interesting kind of pattern here, is that because the function looks like this, it's even function, and of course the eigenfunction like n equals 2, it has a node, and when you calculate the integral to get the coefficient for the psi 2 wave function, it will be very small. It technically should be 0, but numerical error produced some 10 to the minus 16. Now all the odd coefficients are small, smaller than 10 to the minus 2, and they go to even smaller values. Now, this is not very interesting. If we start squeezing the function, let's say put the coefficient 2, and this is, you saw the start, it was like this, part of the parabola in the half of the box. And now it evolves in time because it's a superposition. And the probability density, well, starting from the left, occupies the box. And if you propagate back like in time, then it will start doing some motions all over the box. Now, this is the wave function. And as you can see, there are some, because I'm using finite expansion, you can see that the red dashed curve is it's a smooth curve, but the blue one is the original. It's a parabola on the half of the box, and then it should be 0, right? And I am trying to represent that function by a linear combination of the smooth function, sinusoidal function for the whole box. And of course, in this kink on this part, it's well, like the expansion doesn't really produce a good representation. Now we can also look at the logarithm of the coefficients. Here, not only the first, but the second and third are contributing significantly, because simply we start squeezing our wave function, and kinetic energy grows, so we have more contributions from the higher eigenfunctions. Okay, now we can go to, say, squeeze it 5 times, so we will get really squeezed wave function, and it will evolve faster, occupy the space, and yeah, start kind of developing all these wiggles and so on and so forth. Because it's a superposition state, right? So this is the original function, now squeezed 5 times. It's only occupying 1/5 of the box, and the red one is just a linear superposition of the eigenstates that approximate this. That's what you can obtain if you calculate all the coefficients, and here I use 20 eigenfunctions. So they are doing a decent job, but again, in this area where the function changes very kind of drastically from smooth behavior, from one smooth behavior to another smooth behavior, the representation is not as good. And if we look at the coefficients, now you can see that more eigenstates involved in representing our original wave function, right? So in order to represent this type of function compared to the first one, which was just a parabola occupying the whole box, we need more eigenstates. And we can kind of keep doing that, say squeeze 10 times, and then it will evolve even faster, so the kinetic energy even higher, and it will develop all sorts of these wiggles and so on and so forth. Okay? And this is all very simple simulations, because all you need for them is like essentially coefficients found like an integrals of the original function multiplied by basis function, which is also known sine function. And you need to put the exponents in front of the coefficients, and these exponents, right? And then plot this as a function of space at different times. Okay? Any questions? No? Everything clear? All right, let's consider some applications to chemical systems. Conjugated polyenes, right? So that's the type of system where this particle in the box works very well. All right, let's consider 1,3-butadiene. Okay. And we will assume that, well, only pi electrons are considered, and also they are non-pi electrons only. It's the first assumption. Second assumption is that they don't interact. They don't interact with each other. Okay? And so our box will be the carbon skeleton of this molecule, sp2 hybridized carbons. And in order to calculate what is the size of the box, that's what we need, right? We will use some of the data on bond distance from table. So in this system, so that's why it's kind of not fully ab initio, in the sense that it's not from first principles. We get some numbers out of the experiment in order to do some theoretical modeling. There are methods which all you need is just to put the number of electrons, number of nuclei, and then they will give you a spectrum of the molecule, give the optimal geometry, that sort of stuff. That would be in contrast to this, fully ab initio or from first principles. You don't need to put any experimental information in them. But that would require more work to understand this method. For now, let's just say we want to calculate the size of the box using the tabulated data, and these are in angstroms. All right. So, and then also the last carbon atoms, they consider to be kind of as spheres with radius r, radius of sp2 carbon equal to 0.73 angstroms. So we need to, in order to get the box size, we need to add 2 double bonds, 1 single bond, and we need to add 2 radii of these sp2 carbon atoms. So our box will be kind of including this radii. This is totally empirical, so don't worry so much if you don't completely follow why do we calculate box that way. This is just some prescription that gives reasonable results. Right, so I sum 2 double bonds, 2 radii, and 1 single bond, right? And so together, this all would be 568 angstroms. Okay? And then how many pi electrons do we have? We have 4 pi electrons. 4 pi electrons. And we will use, these are our levels of particle in the box, E1, E2, E3, and we'll use, again, without really explaining why this appears here, we will use Pauli exclusion principle, which means actually, what does it mean? That 2 electrons cannot be on the same state with the same spin, right? Or the same state, essentially, because spin can be considered as a part of the definition what state is. So you know from general chemistry, there is like double occupation of every orbital. We'll talk about spin a little bit later. So right now, again, this is not fully first principles. And so we use some prescriptions. And so the 4 electrons, they kind of occupy first 2 kind of orbitals that are generated by particle in the box problem, right? And if we are interested in studying the excitation spectrum or like optical spectrum of this compound, then we assume that the light comes in and it promotes one electron from the highest occupied orbital to lowest unoccupied orbital, and that energy difference would be responsible for absorption of light, right? So if you are interested in what is the frequency of light that is absorbed by a compound, then you need to calculate energy difference between highest occupied and lowest unoccupied orbital, right? Because that's where the action is. That's where the light comes in and promotes electron from the highest occupied to the lowest unoccupied. Okay? Just the other orbitals will lie even higher up, so the higher excitations are also possible. They will be higher in energy, and let's just focus on the lowest excitation according to this model. So then delta E, this delta energy for this process going from E2 to E3 naturally is E3 minus E2. Okay? And so let's just put the equations that we know from particle in the box problem. What is E3 and what is E2? And then we'll put all the parameters, mass of electron, size of the box, and we'll get what the delta E is. And then we'll recalculate what the frequency of light should be to promote that transition. Now, I have a slightly different expression here for the En, not using the reduced Planck constant, but rather normal Planck constant H. And I'll write down the energy expression for the Planck constant case. The one that I was writing before was like this. And if you recall that h bar is h divided by 2 pi, then you can see that they are the same. Okay? But in my notes, I use this one for this problem, so I'll stick to that one. And the delta E then is equal to h squared divided by ml squared. So our final is first E3, so it's 3 squared minus 2 squared. Okay? Now mass of electron, because that's what we're moving, electron is 9,109 10 to the minus 31 kilograms. Size of the box is 568 10 to the minus 10 meters, so we work in SI units. And then delta E, in SI units, H constant, I'll put it right away. Okay, let me put it here. H is 6.6 10 to the minus 34 joules times second. And that's pretty much all you need, these three constants, right, to express delta E. So it's 6.6 10 to the minus 34 joules second. This is h squared. Then you have 9 minus 4 coming from 3 squared minus 2 squared divided by 8, comes from this 8. And then mass of electron, 9.1 10 to the minus 31 kilograms. 568 10 to the minus 10 meters squared. This is L squared. And if you do all that, then delta energy is 9.3 10 to the minus 19 joules. Okay, and if we're interested in the wavelength of light, then we just need to transform this energy into wavelength. Delta E equals 2, according to Einstein expression for the energy of light. So this delta E is equal to h mu, and we have also relation that this nu times lambda, the frequency of light times the wavelength of light, is the speed of light. So that means this can be written like this, right? And lambda then equals to hc divided by delta E. And if you calculate by putting the Planck constant and the speed of light in meters, then lambda is 213 nanometers. That's the wavelength of light. And experimentally, lambda experimental for this compound, it was found that lambda equals to 17 nanometers, right? So pretty close. And well, this correspondence is pretty fortuitous, right? So it's not that the model works like that everywhere, right? In order to see that this is a somewhat lucky correspondence, we'll consider some other compounds like other polyenes, and you will see that very often whatever particle in the box gives you is overestimating the experimental values. Okay, yeah.
How does this calculation change if we consider resonance?
Oh, it's already considered resonance.
You said they're not interacting.
Right, electrons are not interacting, but the resonance is not assuming some interaction. Right, so resonance is this organic chemistry picture, which in quantum language is nothing but, in order to lower kinetic energy, you need to make things delocalized. Because once you start squeezing your wave function, making electrons sitting on the carbons without jumping to other carbons, then the wave function becomes, as we saw, essentially like a squeezed parabola of the particle in the box, and it just accumulates quadratically energy with the squeezing factor, essentially, right? So that's why in benzene, right, we have this delocalization, which happens because, well, you try to minimize kinetic energy. And in chemistry in general, from the point of view of quantum physics, it's just a game of localization and delocalization of the wave function, because there are two main terms. If we kind of forget about the electron-electron repulsion in this case, there are two main terms in the Hamiltonian of any molecule is electron-nuclear attraction. So nuclei, they create these wells where, of course, the more localized function is, it experiences this deeper areas of that well, the Coulomb well, because electrons are attracted to nuclei, right? So they have propensity to be close to nuclei. That's what forms atoms, right? But then there is the kinetic energy of electrons that essentially tell them, well, go away, go as far away as possible, and that's how you kind of lower your energy. Now there are atoms that have even, well, nuclei that have higher charges, so that's why they try to have like this 1s, 2 configurations which are really localized, and that's why they don't really participate in chemistry, because they are very comfortable, the wells are very deep, and they're just sitting there. Of course, not everything can sit there because we have a Pauli exclusion principle, so they eventually climb up the ladder of this energy because they just cannot all sit in 1s orbitals, right? So once they come here, they don't feel as deep well as 1s electrons feel, and then there is a balance between being close to nucleus and kind of be delocalized, right? And so, of course, chemists, they like everything to be localized. The whole idea of chemistry is that we can judge the molecule by its components, right? So that's purely local, kind of local picture that, okay, if you put the methyl group, then it will act as a methyl group in any compound, right? And that would be really great. Right? But in reality, there is this delocalization that makes every molecule very specific, very individual, right? Because it's like a soup now, right? Because kinetic energy makes all the electrons experience potential of all the nuclei and all other electrons, right? So there's this tendency for delocalization, and this resonance structures is just a chemical language how to explain that tendency for the delocalization. But there is like in quantum physics there are no resonances, right? We can in some models you can kind of suggest analogs of these resonance structures, but in reality there are operators in quantum physics, and kinetic energy is the one that makes delocalization energetically favorable, right? And of course, well, there are other operators. That's why molecules are so interesting, because they have different tendencies. Since their Hamiltonian is not just kinetic energy of electrons, it's also potential energy of electron nuclei, kinetic energy of nuclei, and electron-electron repulsion, nuclear-nuclear repulsion. All those terms, they kind of drive in a different ways, and that's why it's so interesting and complicated. Okay. But going back to particle in the box, it's in a quantum, at the quantum level, what we are neglecting is electron-electron interaction, and we also neglected the, say, 1s electrons. They are sitting in their wells and don't play a big role here, right? Because since they are localized, say, on this carbon, for them, it doesn't really matter how large the box is, right? So it's only particles which are mobile, kind of, in a classical language. Or in quantum language, the particles which are delocalized over the whole molecule, and they also are the pi electrons. It makes sense to consider them in this model. For 1s electrons, model would be not a particle in the box, but rather particle in a very deep well, okay? And that well has certain parameters. It has nothing to do with the overall size of the molecule, right? So the particle in the box is nice because for the pi electrons, because it kind of really gives an idea how to treat complicated systems like quantum dots, or like some people even claim like it can explain why blueberries are blue and cranberries are red. It's all about the size of this dye molecules that define the color, though I'm not completely convinced that you can really obtain red and blue colors. It's here where we got the estimate very well, but those dyes, I saw them. It's not like some one-dimensional molecule. Some blueberries, I think, they are more like a two-dimensional sheets of confused benzene rings. So it's like a 2D aromatic system, and so you would not want to use the 1D particle in the box model for describing those. So reality is more complicated. But as a selling point, these particle in the box models, they can be applied to quantum dots. right? So you can actually make kind of people call them even artificial atoms. So some nanostructures, cadmium selenide, for example, and because the electrons are somewhat delocalized in some of these particles, you can simply see what the color of the particle will be based on the size. And the smaller the size, it goes to the blue region. The bigger the size, it goes to the red region. And those trends are well confirmed and can be predicted by particle-in-a-box model. Okay. All right. So life, of course, is not one-dimensional, and the next point will be about extension of this particle-in-a-box model to 3 dimensions. Okay, and that extension is pretty simple because we will take advantage of the fact that operator, the Hamiltonian, for so-called 3-dimensional particle in a box, that operator is separable operator. So generally, I want to remind you, we use that for reducing the time-dependent Schrödinger equation. All right. We talked about this separable operators, essentially, when you have operator of one variable plus operator of another variable. Then you can solve eigenvalue problem which is a very important problem for quantum mechanics. If you can solve problems where operators acts on a wave function gives you constant times a wave function, then essentially that's the core of quantum mechanics. Then you solve the problem. Now, unfortunately, not all problems are like that, where when you have many particles, then the Hamiltonian is just a sum over the Hamiltonians of individual particles, right? Or in this case, Hamiltonian is only operator dependent on the space. There is a time-dependent operator, and then we can solve this problem. If we know the solution of O1, say phi n of x, right? And O2, say theta m. Right, we spoke about this. So in the situation when you can split overall operator into 2 pieces and there is a addition of those 2 operators, then knowing the solution for each allows you to combine them in a very simple way. The psi is essentially, the wave function is a product, and okay, and the eigenvalue in this case is just a sum of eigenvalues, right? So there is this simple relation that you can check that that's the case, and we use that already. Now for a particle in the box with 3 dimensions, we have a very similar situation, where all 3 dimensions are independent. So we'll be solving again on the time-independent part, okay? But our Hamiltonian will be Hamiltonian, say, I'll call it A of x, which will be particle in a box in x direction, h of b And it's a particle in the box in y direction, C in z direction. Okay. And then wave function that depends on all three dimensions is just a product of wave functions for individual dimensions, and energy is a sum okay, and the same thing for C. All right, so now what is the geometric construction? So geometric construction would be for the 3D like this. We have a 3D box. Right? So we have 0 here, y, z, x, and inside we have a potential equals 0. Outside we have potential infinity, and the box dimensions are corresponding to A, B, L subscript A, L subscript B, and L subscript C, right? So this is our potential, essentially V, X, Y, Z equals to two values, 0 and infinity. 0 if X within the 0L A, and y at the same time between 0 and LB, and z is within 0 and LC. Infinity when one of these conditions is violated. So violation of the conditions you cannot use AND operators, right? You should use OR operators. So it's either X not in the range or Y not in the range or Z not in the range, right? Because it's enough for the potential to be infinite when one of these conditions is satisfied, or several of them at the same time, or is still true if X is not in the range and Y is not in the range, right? Or three of them outside of the range. But AND requires so that X and Y and Z, they were all in the range. Okay. Now the equation for the wave function will be essentially on our time-independent Schrödinger equation in the operator form will be written as sum of the kinetic energies. Okay, plus 0 potential, x, y, z gives energy psi x, y, z. Okay, so this is the equation where clearly you have 3 operators, so they all depend on their own variables, x, y, and z. There's no potential, right? So then, in order to solve this equation, all you need is to solve individual equations for x, y, and z, and then individual equations would be particle in the box problems for one dimension, right? And then you can make the products of functions for one-dimensional problems in order to make the three-dimensional wave function, and in order to get the energies, you just sum the energies of one-dimensional solutions. One thing to, of course, remember is that there is infinite number of solutions per dimension, right? So in X you have infinite number of solutions. In Y you have infinite number of solutions. In Z you have infinite number of solutions, right? So then you need to really keep track of what are the solutions you are combining to make the solution of the total problem. So one way to keep track of all that would be proper indexation. So if you have say if you want to talk about a specific solution of three-dimensional problem, you need 3 subscripts, and x and y and z, right? And that will be you kind of take this 3 normalization factors for each dimension, right? So 1 for each dimension was square root of 2 divided by L. So you have 3 of them. You got 8 divided by product of all the dimensions. And then you have sinusoidal functions per dimension, and x by multiplied by x, L, A, it's 1 times sine of ny by LB y and corresponding energy also has 3 subscripts, and okay, and then of course nx, ny, and z, they can run from 1 to infinity, each of them. Okay. Any questions? Do you recognize the sum over individual energies for each dimension? It's like if it were a one-dimensional problem, that would be the energy, right? And this would be a wave function, right? But because we have three-dimensional problem with separable x, y, z, then we can write total wave function as a product. and total energy as a sum. And so in the last 5 minutes, what I want to talk about is so-called degeneracies. It's not that complicated. It's just when you have some symmetry in the problem, meaning that let's assume LA equals LB equals LC equals L. So let's consider the situation where we really look at the particle in a cubic box, right? So that will make the box that we're considering is of this cube symmetry, right? Cubic box. Then in this situation, if we just apply or like consider this condition for the energy expression, then energy for the cubic box, we can take L, A, B, C outside because they're all the same, and the energy would be H square 8mL square nx square plus ny square plus nz square. Okay? Although the box is symmetric in x, y, and z direction, there is still these numbers nx and y and z which are separate. Why is that? Because we have coordinate system x, well, it has axis x, y, and z, and you see that although energy levels can be so-called degenerate, what do I mean by that? Is, let's say, if we plot the energy, then the first level will correspond to nx and y and z all 1, 1, 1. That's the lowest you can get. Then the next level, or actually 3 levels, will be 2, 1, 1, 1, 2, 1, and 1, 1, 2. These 3 numbers that I'm writing here is nx, ny, and nz. Right? And they all like, because it's just the sum of the squares, they all have the same energy. If you sum 2 square plus 1 square plus 1 square, or you do this in this sequence, right? So they all give, what, 6, right? Now, why are we separating them into 3 levels? Energies are the same, but our wave functions corresponding to these levels, 2, 1, 1, 1, 2, 1, 1, 1, 2, they all look different because we saw from the 1D problem psi 1 looks like this, and then if we put the 0 line above so that they won't go on top of each other, the 2 looks like this with a node, right? And that was the x direction, right? And this is a function. Now, this function has a node in x direction because it has 2 quanta in this x direction, and it has no nodes in y and z. In y and z it looked like this, in x direction it looks like this. Okay? While this function has a node in y direction and has no nodes in x and z direction. And this function has a node in z direction and no nodes in x and y. So the functions look differently because simply, well, they are products of, say, psi 1 x, psi 1 y, psi 2 z, right? So if you write down this function in terms of sign functions, you can see that nx and y and nz, they always, well, will affect their own coordinates, right? X, Y, and Z. But energies for those three are the same. And we can continue. This is essentially level with degeneracy free, because there are three different functions corresponding to the same energy. And then you can go to the next level, also triply degenerate. So it's 2, 2, 1, 2, 1, 2, and 1, 2, 2. Here it's a kind of reverse situation. You have no nodes on Z, on Y, and on X, right? And one node on all other coordinates. And the energies, of course, will be the same. Then, yeah, so you can go ahead and, in my notes, actually, there is a energy diagram which illustrates the degeneracy. And in problems like, I think I'll start with chemical bonding in the next lecture. But in the problems which will be offered in exams, you probably will be offered something like the two-dimensional box with the same dimensions. What's the degeneracy of the first level or second level, right? So for that, you just need to consider, okay, these levels and see how many different functions can you put for the same energy, okay? So for example, degeneracy of the second level is 3, degeneracy of the first level is 1, degeneracy of the third level is 3 again, and so on, okay? Any questions? Good.